Hello everyone. Let's solve the next question from equilibrium of beams where we have a trapezoidal load involved in the question. Let's read the question. A beam supports load varying uniformly from intensity W1 kilonewton per meter at left to W2 kilonewton per meter at the right end as shown in the figure. If the reaction RL represents reaction at the left, so which is nothing but reaction at A. RL is 6 kilonewton and RR, that is reaction at the right side, which is representing the reaction at point B, is 12 kilonewton. Now in the diagram we can see that the support at point B is a hinge support, and at A we have a roller support. We know that hinge has two reactions, horizontal and vertical, but still here we have only vertical reaction given. Now by this time you must have guessed the reason why. We can see here we have a trapezium loading which we are going to convert into two equivalent point loads which are going to be vertical in direction. So in the entire system we don't have any horizontal or inclined force. That's why the horizontal component of the hinge is going to become 0. Considering this and with the given information, let's try to find out how much is going to be the intensity W1 and W2 for equilibrium of this beam. Let's construct the FBD. Let's convert in the FBD. Now basically we have to convert the trapezium into one rectangle and a triangle and then to the equivalent point load. So let's draw that. So we have got the total length 3 plus 5 plus 4, that is 9 plus 3, that will be 12 meters. So the total length of the beam is of 12 meters. Let me draw the beam AB, which is total of 12 meter. Point A, which is 3 meters away from the left end, has a known reaction Ra 6 kilonewton. Then after 5 meter distance we have got known reaction Rb, which is 12 kilonewton. So this is end A, sorry, this is not the end, this is the point somewhere in the middle of the given beam, and then here again the point B, and these are the reactions. Now let's convert the rectangle and the triangle into its equivalent point load. We know that we are going to divide the trapezium into its two shapes. One rectangle at the base which is having height W1, and now the remaining height of the triangle is going to be the total height W2 minus height of the given rectangle W1. So for the triangle, only for the right angle triangle which is remaining on the upper side, once we have removed the rectangle, the height of this triangle is going to be W2 minus W1. Of course that is going to be into in units kilonewton per meter only. So this is the height of the given triangle. Based on that, now let's find out position of equivalent point loads representing the rectangle and the triangle. First let's consider the rectangle. For rectangle, whatever is the total spread of the beam, we said it is of 12 meter. Exactly at the midpoint, we are going to have point load. So let's represent it over here such that the position of this point load, which is representing the rectangular load, the uniformly distributed load, will be exactly at the midpoint. So if the total length of the beam is 12, it should be 6 meters from either ends. Let's represent it over here. And the magnitude of the point load is going to be area of the rectangle. So W1 into 12. So that is 12 W1 kilonewton should be the magnitude of the point load. Now let's consider the triangle, where height of the triangle we said is W2 minus W1, and the base is nothing but the total span of the beam, 12. We know that when we convert a triangular load into its equivalent point load, the position of the point load has to be located from the right angled edge at the base at position L by 3. So now the total length is 12. So 12 by 3, that should be 4 meters. So 4 meters from the maximum height position, if you locate the point, it comes out to be at B itself. The point B is present from the right end of the given beam at distance 4 meter. So at exactly the same position here, we are going to have the location of point load representing the triangle. And we know for a triangular load is also called uniformly varying load. Area of the triangle is going to be the magnitude of the point load. Now area of the triangle is calculated as half into base into height. Height is, we said, W2 minus W1 into the total length of the beam itself is the base, which is 12. So that comes out 6 in bracket W2 minus W1 in kilonewton. So we have got the beam, the loads which are applied on the beam, and the supports. The support reactions are already given to us. Let's represent the given dimensions as such. 3 meters from A to B, distance is 5 meters, and from B to the end is 4 meter, and this 4 meter distance is also the position of our point load representing the triangle from the right hand side end of the beam. Fine. So here our aim is to find out W1 and W2. Clearly we can see that we'll have to use two conditions for finding out these two unknowns, W1 and W2. Let's begin with summation Fy equals to 0. Because all the given forces are vertical, we cannot use summation Fx equals to 0. That is not going to give us any unknown from the given equation, from the given question. So let's apply summation Fy equals to 0. So we will have 6 minus 12 W1 minus, now let me solve this bracket. Fine, let's write down the bracket as such, and then later we will solve it. W1 minus W2, so there won't be any confusion of the sign. And then we have RB, which is 12 and going vertically upward. As you know, while applying condition summation Fy equals to 0, we are taking upward positive and downward negative. Let's simplify this further. So 6 minus 12 W1, solving the bracket, minus 6 W2, minus into minus, that will be plus 6 W1 plus 12. Let's get all the unknowns on one side and the variables on one side and all the constants on the other side. So we will have, let's bring all the terms of W1 together. So we have minus 12 W1 plus 6 W1. So that will be minus 6 W1 minus 6 W2, and then 6 plus 12, that will be 18, and that we are going to bring on the right hand side of the equation. So that will be minus 18. Okay. So here all the terms are negative. So we can say 6 W1 minus 6 W2 rather plus 6 W2 is going to be equals to 18, or rather you can also see each and every term can be divided by 6, and we will have W1 plus W2 equals to 3. Let's say this is equation number 1. So using condition summation Fy equals to 0, we have got one relation between W1 and W2. We need to generate one more equation so that we will have the same two unknowns, W1 and W2, or let's say at least one unknown should get solved by using another condition so that we can solve these two unknowns. Okay, so the only left condition is the condition of moment, summation M equals to 0. We have to look for a fixed point where we can apply the moment. Now here, either you can apply the moment about point A or about point B, so that one unknown, either W1 or W2, will not be there in the equation. Rather here, if I apply a moment about point A, both the unknowns will be there in the equation, and that equation we can solve simultaneously with equation number 1. But we have one advantage if we apply moment about point B. If we apply moment about point B, the load 6W2 minus W1 is applied at point B itself, so its moment is going to be 0. So in our equation, only W1 unknown will be there. W2 will not be there in the equation, so W1 will get solved and we can substitute it over here in the equation. Let's see. Let's apply condition of moment about point B. Anyhow, point B is one hinge also, hinge supported point. So taking anti-clockwise positive and clockwise negative as usual, let's consider all the forces and calculate their moments about point B. Starting with the reaction Ra 6 kilonewton. 6 multiplied by, from point B up to point A, the distance is 5. Remember, we are calculating moment about point B. We have to measure all the distances from point B. So 6 into 5, rotation is going to be clockwise, so that we will have minus sign here. Then we have the force 12 into W1. It should be multiplied by the distance. Now, how much is that going to be? Position of this 12 W1 from the end of the beam is 6 meters, whereas from end of the beam up to point B, this distance is 4. So here, this remaining distance from point B up to the 12 has to be 6 minus 4, that is 2 meters. So let's multiply by 2 meter, and the rotation of this load about point B is going to be anti-clockwise, should be taken positive. Here both these loads, rather this vertical load 6 into W2 minus W1 in bracket and the reaction RB, both are applied at point B, so their moments are going to be equals to 0. So this is all we have in the equation of moment. We are going to write down this as 24 W1 equals to 30, and this W1 is going to be equals to, let's see, W1 is going to be equals to 24 divided by 30, and that comes out 0.8. So 0.8 kilonewton per meter. Remember, W1 is not a load, it is intensity. It is measured in kilonewton per meter. So W1 is 0.8 kilonewton meter. One of the answers from equation number 1. We substitute this value of W1 in equation number 1 and we get 0.8 plus W2 equals to 3. So W2 is going to be equals to 3 minus 0.8. That comes out 1.2, rather 2.2. 2.2 kilonewton per meter. Okay. So this is what our final answers are. The intensity on the right side, that is over here, W1 is 0.8 kilonewton per meter, and intensity on the left side of the beam is 2.2 kilonewton per meter. These are our answers. Thank you.